Let's analyze the uniform cross-section fin. So we have from before the general expression for the temperature in a fin. So this is the general expression for the temperature as a function of x. So this is a differential equation, second order differential equation. And let me rewrite a couple of things. So I'm going to take these two terms and I'm going to factor h dAs dx. I'm going to put this back together. So we have minus k/ac, the second derivative of t with respect to x, minus k dt dx multiplied by the derivative of the cross-sectional area with respect to x. And now these two terms together, it will be h plus h multiplied by dAs dx, and as a factor of T infinity minus Ts. And this should be equal to 0. So now what I want to analyze, what is T AS and what is AC. So the cross-sectional area, it is going to be this in the case of a uniform cross-section, and because it's uniform, so it is going to be constant. So if this is AC, so AC, it is going to be equal to a constant, and therefore the derivative of AC with respect to x is equal to 0. On the other hand, the surface area, AS, it is going to be this one that I'm highlighting, the one on the top, the one on the side, the one on the bottom, and the one on the other side. So this is the surface area, so this is A of S. AS. So AS, as a function of x, it will depend because it will be equal to the actual perimeter, this perimeter that we have here, multiplied by x. So all this blue area, we can decompose it as the perimeter of the cross-sectional area multiplied by x. So let me write it. AS as a function of x, it is going to be equal to p multiplied by x. So the derivative of AS with respect to x, it is going to be equal to p. Now, with these two values, we can simplify in our previous equation. And so we have that the derivative of AC with respect to x is equal to 0. So that's equal to 0. The derivative of AS with respect to x is going to be equal to p. So this is going to be equal to p. Also, we know that T infinity minus Ts, it is going to be equal to minus theta of x because of the definition that we have from before. So we have T of x is equal to T minus T infinity. Okay, so this is going to be T as a function of x. So we can rewrite this expression. So we can rewrite this expression as minus k multiplied by AC times the second derivative of t with respect to x. The next expression is 0 plus h multiplied by p multiplied by theta of x. Also I can replace in the derivative, I can replace t by theta. So let's do it. So this could be equal to theta, a function of x. So this is a second order derivative differential equation. Okay, and this should be equal to 0. So how do we solve a second order differential equation? So we can simplify it a little bit, the coefficients here, if we realize that these are constant and these are constant. So let me move the coefficients in the following way. So we can divide by minus KAC, and so we have the second derivative of theta with respect to x minus HP divided by KAC and multiplied by theta equal to 0. So if I define M as equal to HP divided by KAC, so what I have, it is the second derivative of theta with respect to x minus M, and let me define this as M squared. The reason why I define it as M squared is doesn't really matter, it's going to be a constant, and all of these are going to be positive. H is positive, P is positive, K is positive, and the R is positive. So M squared is just highlighting the fact that the constant is positive. If I read it that way, I don't have to square root in the next step. So this is going to be equal to M squared multiplied by theta and equal to 0. So that's the differential equation for a uniform cross-section fin. Now, how do we solve it? So, do you remember how do you solve this equation? So you can take a time and try to remember how to solve it. And the answer, it is one of these cases. Okay, let's assume that you took your time to look into the solution. So if you remember from your differential equation class, so this is a second order constant coefficient equation. So the auxiliary equation, it is lambda square, because of the second derivative, minus M square equal to 0. So we solve this algebraic equation for lambda, and so we have lambda square equal to M square. So square root at both sides, so we have lambda is equal to plus or minus square root of M square. So lambda it's equal to plus M or minus M. So we have two different roots. One is M and the other one is minus M. So the solution of the differential equation, it is Z. So this is the case when we have two different roots. So it is theta of x is going to be given by C1 multiplied by e to the minus mx plus C2 multiplied by e to the mx. So now we have to solve for the two constants. So we need two boundary conditions. So we have our fin, so this is our fin, and I'm plotting the temperature on top. So this is the blue coordinate system correspond to the temperature in the y, and x is the distance from the base. So this is going to be the base. So TB is the temperature at the base. So initially the temperature, it is going to be at this point, TB, and T infinity, it is the temperature of the air or the fluid around. So the temperature distribution, it is going to be something like this. So it is going to drop from TB and is going to, at the tip, it is going to be very close to T infinity. But it is not going to be equal to T infinity unless we make this fin very, very, very long. So we need to work out the different possibilities for the conditions at the tip. So we know that the temperature at the base, it is going to be equal to Tb. So what we need to know, it is the temperature at the base. So we can have different approximations for the temperature or for the conditions at the tip. So again, so we are going to look to the conditions at the boundary conditions. So we have the base. In the base, x is equal to 0, and we have that theta of 0, it is going to be equal to Tb minus T infinity. So that means that theta of 0, it is going to be equal to theta b. So let me write this one. So theta of 0, it is going to be called theta b. By convention, that's what we have. So this is one boundary condition. So this is boundary condition. Now the boundary condition at the tip, so we can have either convection, in which we are going to consider that there is convection. So there is a convection boundary condition. So we have T infinity and U infinity on the tip. So we are going to be concentrated on the tip. Adiabatic. In the case of adiabatic, we are going to assume that this is going to be insulated. So that's going to be insulated. So in this case, it's insulated, and then fixed temperature or prescribed temperature. We know the temperature here, so we are going to say T of L equal to TL. And infinite fin, so we are going to assume in the last case that the fin is very, very, very long. So it is as long as that we can assume that the temperature at the length, it is going to be equal to T infinity. So we are going to assume that T of L, it is going to be approximately equal to T infinity. So let's go back to the first one. So in the first case, we are saying that there is convection boundary condition. For convection boundary condition, we have that minus K multiplied by the cross-sectional area multiplied by the theta dx at x equal to L. It is equal to H multiplied by the area multiplied by theta of L. Remember that theta of L, it is T, in this case will be TL minus T infinity. Now for the case of the adiabatic, the second case, so we have that the heat transfer rate, which is minus K times AC of the theta dx at x equal to L, it is going to be equal to 0. So this is probably going to happen in a very thin plate. Very thin plate. We can assume that the convection is not very much. So this is like the more general case in which we are considering the convection in this case. So when can we consider like there is not heat transfer? Well, when there is a very thin plate. So the area is going to be very, very small, so we can assume that this is actually equal to 0. Now, fixed temperature, TL equal to TL, when for some reason we know it, because this is connected to another body and we know the temperature. So this is a very particular case, but in this case we have that theta of L, it is going to be equal to theta L. So this is known, or in other words, prescribed. And finally, the last case in which we are assuming that the fin is very, very long. So we are saying that theta of L, it is equal to T infinity minus T infinity. We're assuming that the temperature on TL is equal to T infinity. So that's going to give us that theta of L is equal to 0. Okay. So depending on these boundary conditions, we can solve the differential equation. So remember that the differential equation that we have, let me write it here. So we have that theta of x equal to C1 multiplied by e to the mx plus C2 e to the minus mx. So that's the differential equation that we are solving. Depending on the boundary condition, so we have, in the book they call it A, B, C, D case. So remember that m is defined as m squared equal to hp divided by kac. Here they are defining another constant, uppercase m, equal to square root of hp kac multiplied by theta b. So that theta b, it is out of the square root. So we can have the temperature distributions, the solution of theta of x. Here the expression is theta of x divided by theta b, and the heat transfer rate. So we can see that the first case, when we consider convection, so we have a very complex expression in terms of hyperbolic cosines and hyperbolic sines. And also the heat transfer rate is given in terms of hyperbolic sines and cosine. So this is the more realistic boundary condition, but it will give the more complex equation. So the second one is the adiabatic. Remember, the adiabatic is when we consider that the fin is very thin. So the temperature distribution, so theta divided by theta b, it is just cosine, hyperbolic cosine of m multiplied by L minus x divided by hyperbolic cosine of m multiplied by L. When we have prescribed temperature, so we have this expression, and the heat transfer rate is given by this expression. And in the case of the infinite fin, so in the case of the infinite fin, so when the fin is very, very long, and probably thin also, so we can consider that the temperature distribution is just e to the minus mx. So this is the most simple mathematical expression for the temperature from all of this. Also, the approximation is quite big because we are assuming that the fin is very, very long and thin also. And the heat transfer rate is just given by m. So these are the possible solutions for the fin. Thank you.